Okay, so welcome to the channel, guys. Today we are gonna read about macroscopic and microscopic viewpoint in thermodynamics. And the second topic we will cover is different types of thermodynamic systems and understanding control volume. So, what is microscopic and macroscopic viewpoint? So, first let's see macroscopic viewpoint. Macroscopic viewpoint, and I will also have microscopic viewpoint here. And let's actually first begin with microscopic viewpoint, then we can describe macroscopic viewpoint because the one comes after the other. Microscopic viewpoint, so if I'm talking about microscopic viewpoint, just imagine I am actually interested in properties of a gas or in properties of anything, my surrounding, by observing the molecule or what the atom is doing. But atom will be too basic or too fundamental, so let's consider a molecule which is more stable. Atom is not stable, so molecule will be stable. So in microscopic viewpoints, I am interested in observing observing my environment of interest with a approach or with an approach where I am studying behavior of molecules behavior of molecules and its effects on system. So in microscopic viewpoint, I am approaching any problem on a molecular level. I'm trying to see what is happening to the individual molecule. So let's say if I'm trying to see the boiling phenomena. So if I'm doing a microscopic study, if I'm having a microscopic approach towards the boiling phenomena or the problem of boiling, I will be interested in knowing how each molecule of water is getting affected by the heat. So, how each molecule of water is getting affected by the heat. So, I want to know this is molecule, let's say 1, molecule 2, molecule 3, 4, 5, how this molecule of water is getting affected by heat, how this is getting affected by heat. And we know that each and every molecule will have a different effect. So, I'm actually interested in the more of a molecular level, and I'm studying that in a microscopic viewpoint. So this is what microscopic viewpoint is. In such type of study where we go to a molecular level or to a very small unit or a quantity, our area of focus is just a single molecule and studying its effect. That type of thermodynamics is known as statistical thermodynamics. Statistical thermodynamics. Now, now comes macroscopic viewpoint. So this is more popular. I mean, in the basic thermodynamics, when you're studying the fundamental of thermodynamics, you will be addressing the problems as a macroscopic. You will be having a macroscopic approach to the problem rather than having a microscopic approach. But we can derive all the results of macroscopic approach from the microscopic approach. Now, what macroscopic approach is, I'm not interested in a single molecule. So rather than if I'm addressing the same problem like the boiling of water, so rather than seeing how the individual molecule is behaving, I'm actually interested in knowing how this collective group of molecules is behaving and how it is affecting the system. So let's say if I'm studying about pressure, which is force applied per unit area, I want to know how the force is applied by a collective molecules having a large approach. And a microscopic viewpoint or a macroscopic viewpoint approach is important because now you can feel it, you can measure it. Because let's say if I want to ask you, can you measure the temperature of molecule 1 at, let's say at time t1, the temperature will be 30 degrees, but now it starts to boil at time t2, it should be around 100 degrees. But I say, can you measure the temperature and tell me what it is? Is it 100 degrees, 99 degrees, 99.99 degrees, what it is? So you can't connect a thermometer here and just tell me the temperature of this molecule, because humans have not developed such device where we can go to such minute scale, because we ourselves are a collection of different molecules and we are seeing our environment as a macroscopic approach. We are taking a macroscopic approach towards the environment. So that's why we have instruments who cannot go to do such a study where I'm taking a temperature of a single molecule. I mean, in a sophisticated lab or a research lab, you will have such equipments, but in general day-to-day activity, you don't have anything where you will have a microscopic approach towards this problem. Whereas if I say, if you now approach this as a macroscopic viewpoint, and I say, can you tell me the temperature of this quantity of molecules or this quantity of water, you will just place a thermometer here, take the temperature, and tell me the temperature simply. So these can be actually measured with the equipments we have right now. And let's say if you're trying to measure pressure, you can simply connect the pressure gauge and measure the pressure. So these are the something which we will can measure through the equipments we have, and we are taking a larger viewpoint on this. Okay, now it is important to know that the macroscopic approach or the macroscopic results, let's say if I'm going back to the same problem, pressure is equal to force per unit area, and let's say this pressure at some particular uh, system, I find that I'm applying this force at this particular area here, and I'm interested to know what is the pressure on this. So the pressure will be simply the applied force upon area, which is length into breadth, this cross-sectional area here. So I can simply say, okay, this is the applied pressure, which let's say comes about to be force is 10 Newton, area is something meter square, 10 Newton per meter square. Let's say it is 1 meter square. Now, if I take it to a microscopic approach, I will actually see what is the force applied to this molecule, what is the force applied to each single molecule. If I go back to the microscopic approach and I'm enlarging this area here, so I'll be interested to know what is the point force applied to each single molecule on this surface and how they react. So what is the response of this? So maybe the pressure on this, the force applied to this while I'm applying the force is not 10 Newton, but it is maybe 9 point something, 5. And this area is something, it will be in a very minute scale. So let's, for the sake of something, just take 10 to the power minus 9 or 8, whatever. So this is the force applied at this point. Now, what is the force applied at this molecule. Similarly, it could be 9.5 divided by this. Similarly, things will be different. It could be 7 by 10 to the power minus 12, could be 6 by 10 to the power minus 15, and remaining. It will go on till we complete all the molecules. Now you cannot address a physical problem in your day-to-day activity with a microscopic approach because it's become so tedious. But if you actually see this is more accurate way, this will, if you sum this up, you will approach to 10 Newton per meter square. This will be the final result because when you are summing this up, you are seeing the effect of all the molecules combined. So these are the macroscopic viewpoint and microscopic viewpoint. Now there is a second topic which we mentioned, which is what types of thermodynamic system. So let's go to that types of thermodynamic system. Okay. So first of all, we want to know what is a system? What is a system? What is a thermodynamic system? So I'll just say what is a thermodynamic system. So a thermodynamic system could be an area or a region where focus or attention is paid for analysis of a problem. So let's say this is an area in space and we are paying attention on this particular area. So we will call this a thermodynamic system. Or it could be a matter in space. It could be a particular matter we are paying focus on, and this particular matter can be called as system. Now, why to come up with these things? Why to design such cumbersome things? Because if you are approaching a problem, you can imagine, I mean, when brilliant minds derived thermodynamics and formed the basic formulations, they are interested to come up with theories and fundamental equations which are required, but they need some kind of assumptions. So an area is considered so that now all the problems can be designed around this area. So this is just a hypothetical area. Now, in your actual problem, let's say you are working with an engine piston and there is a engine here. This is a cylinder and this is a piston which can go up and down on the cylinder. And over here you have your fluid. Now this can be compressed, so you can decrease and increase the volume. So this, if you are studying this analysis and I'm saying how does this expansion of fluid is affecting the outcome or the power we are obtaining from this engine. So you will design this particular area, you will define this as a thermodynamic system, and then you will begin your analysis. Then you will see, okay, what is happening within this area? Because now there is a cylinder head connected here. There is so many different attachments connected to the engine. I'm not interested. I'm taking it step by step. So I just define one single region here and I will do my analysis here, then move to the next step. So my first step will be to define a thermodynamic system here and do my analysis in this area, see what is the effect here. That's why such concepts are made. So when we study about thermodynamic system, it is important to know whenever there is a region in space or matter, it will have a boundary. So this boundary is actually within which the system is, or this boundary is the shape of the system, you can say. This is where the system exists. So now you have a system, the surroundings, everything external to it's called its surrounding or environment. So this is the boundary of the system, which will is the shape of the system, and everything external to the system is called surroundings. or environment. So this is how the thermodynamic system is defined. And together, the system plus its boundary plus its surrounding and environment, this is called a universe. Okay, easy to understand. So now we move on to the next step, which is to understand how many different types of system we have. So a thermodynamic system can be a closed system, closed system. It can be a open system, or it can be a isolated system. Now, what is a closed system? A closed system is system where there is no transfer of mass. So, if we talk about closed system, the energy can flow. Energy in, energy out. Okay, and this, what is this? This is the boundary. But there is no mass transfer. So, in closed system, there will be no mass transfer, and this is important to know. Energy can transfer in and out, but no mass transfer. Now we come to open system. So what is open system? In open system, the energy can come in, energy in, energy out. Also, the mass can come in, mass out. So there is a flow of energy, there is a flow of mass, and this particular is the boundary or the shape of the system. So mass transfer plus energy transfer. Just think about your air compressor. So you're giving air, it is compressing the air, and then it is releasing the compressed air. So there is a flow of energy, there is a flow of mass within the system. So that's an example of an open system. Now, on the same hand, if you think about closed system, if you think of a cylinder and a piston arrangement, so this is a piston of a locomotive and this is the cylinder of a locomotive. When you have fuel here, this piston can move up and down, but there is no incoming of mass. Mass is fixed. Mass is fixed, but energy can flow. If you raise the temperature, there will be increase in energy of these molecules, and that's why it will push the piston away, and that's how you get the rotatory power in the automobiles. So energy can flow in and out, but mass will not flow. This is an example of a closed system. So now there is third, which is isolated system. Now what is isolated system? Isolated system, there is no transfer of energy, no transfer of mass. This is the easiest one. Nothing to worry about. No transfer of mass and energy. The easiest. So these are the three types of thermodynamic system which we need to know of. One is a closed system, one is the open system, and the third one is the isolated system. All your thermodynamic problems will be focused around or revolve around these three systems. Now, after we study the thermodynamic system, there is something which is known as control volume. Control volume. So what is this control volume actually? So to define a control volume, if we are doing a study of an open system, study of open system, where energy can flow and mass can flow. Both energy and mass can flow. So if you're doing such a study, if you're doing thermodynamic analysis of such system, we will pay focus or we will pay attention on a certain volume in the space. And that's why that certain volume in the space is known as control volume. Just an example, we take this air compressor. This is an air compressor. You are supplying air which is getting compressed in, and then it is getting compressed, and then you are getting high pressure air from the other end. Now there is some other equipment which is running this air compressor, which will be motor. So we are paying attention on a certain area for this analysis in an open system. So for that, the area under this red zone is my control volume. And the boundary of this control volume is known as control surface. So basically, you can say now you would say, okay, this is what the definition of open system is. And you're right. Open system and control volume are the same thing. But for a thermodynamic analysis, we consider it a control volume. In an open system, we take an area of a focus and then we work around that area. And that's why we call it a control volume. Because a system could be the whole system. This all could be a whole system where my motor is running, is connected to the air compressor, and everything is going in. But I'm only interested in this area and then I will analyze this area. So first I'm interested in seeing what is happening in this area. I'm supplying work which is getting converted to heat and compressed air. So work is supplied through this motor. So this particular area of focus is control volume. Now there will be another area of interest of focus which will be a motor. That could be another control volume. And this whole system is known as open system. So just to make things easy, open system and control volume are the same thing, but you can say control volume is like a child of an open system. So open system is large and it is large enough that if you're doing a thermodynamic analysis, we need to pay attention on one area first and then other area and then see the combined effect of that. So that's why you define another term for it, which is called control volume and control surface. So this is what control volume and a control surface is. It is important to know that whenever there is a matter flow, then the system will be matter is flowing. It is an open system. The system is known as to be a system of a volume of a fixed identity, or which is a control volume because the volume is controlled. But now we are saying that matter is flowing in and out. So we will say because the volume cannot get more than that. So the volume is controlled. How? Because the air compressor, even if I'm supplying air to it, air compressor boundary is not stretching. It is not stretching its volume. It is not increasing in dimension. It is decreasing the space between the molecules of gas or increasing the pressure on other hand. And that's why it is increasing the internal energy of the gas. And we are supplying that higher energy gas from the outlet of the air compressor. So we are decreasing the volume. We are sorry, yeah, decreasing. We are keeping the volume fixed, and we are supplying the mass in, but we are trying to keep the volume fixed. That's why the mass, which is additional mass, which is supplied, there has to be a compensation for that, and that's why the space between the molecules is decreased, and now that's why you achieve compression process. So that in that kind of thing is known as volume of fixed identity. Whenever there is a matter flow, if I'd say M1 is and M2 is flowing, so whenever there is matter flow, we say system to be volume of fixed identity. So now we are talking about the control volume. Okay, these definitions are relevant for control volume. Whenever you say this is a control volume, but you say the matter is flowing, we will say that this is a control volume of fixed identity. This is a volume of fixed identity. Simple. And closed system is similarly a system which is close to the matter flow. There is no matter flow at all, though its volume can change against a flexible boundary. If the boundary is flexible, volume of the system can change. An open system and control volume are same, but control volume could be a child of open system. So on this lecture, we will stop here, and then we will continue the other topics on the next lecture, which will be basic thermodynamic properties, processes, and cycles, and try to understand what those are. So if you like this video, please do share and subscribe to the channel, and we will see you on next video. Thank you very much.